Welcome everybody to Ultrasound Physics. This is your first lecture. All of our lectures will be online and they're going to be split up by chapters and then grouped together by units. So we're going to start with chapter 1 today. Now the book that you will need for this class is called Understanding Ultrasound Physics. It's the 4th edition by Sidney K. Edelman and it is green. If you go on if you go on to Amazon or some other used book places, you might see a copper edition running around. That is the 3rd edition. While it has a lot of the same information, it's not going to be set up quite the same way and your pages might not match. So the green one is what everything is set up for currently, but if you needed to get an older version, it will work. Now, I cannot stress enough how important this book is. Read the book. You might be thinking to yourself, oh, textbooks are boring, I can't put up with it. Edelman actually does a really awesome job about breaking the information down, giving you examples, giving you pictures, and giving you charts, and just a lot. He just organizes it so well. I cannot stress enough how important this book is going to be to read it. So that being said, every week you are expected to read the chapters that are assigned. I will be lecturing, and I'll basically be lecturing from the book. So a lot of the terms, the order that we go on things, it's all going to be from the book. And I'm just going to try to use different analogies or use different explanations or just kind of recap what you've heard or what you've read in the book so you can hear it a different way. The other thing that you'll find in the book, again, I cannot stress this enough, that you go through it. There are going to be section reviews and chapter reviews. Do these questions. These are going to be huge. You get to practice questions, see if you understand what's going on, and then the answers are right there with a brief description. Now I have other videos that I went through question by question and also did descriptions and did the math and did examples with them. If you're interested in seeing those, I can send you the links. I have not quite decided if I'm going to post them or not, just because they are embedded into some old lectures of mine. But I do have a way to get them if you guys think that'll be helpful, so let me know. Again, we're going to go chapter by chapter. Awesome pictures in here. The last thing that I want to point out is at the very end of the book, after chapter 24, is a whole bunch of review questions. So that starts on page 423. There are like 800 and some, I think. Let's see, how many are there? It follows the same setup, and it follows each section so you can get practice on getting ready for your boards. 629 questions. So that whole section of the book, that is practice. And it's going to be so important that you practice. So a big part of that you're going to see throughout our classes that we are doing some practice questions. So you guys are going to practice writing questions. You're going to practice each other's questions. You'll be taking quizzes weekly on the material that we've had. There is a mock SPI board at the end of this exam, and then there's your final. So there's lots of opportunities to practice questions, and I think that is going to be a huge part of your success, is understanding how to answer these physics questions. Now, a big part of your success too is also going to be that you actually understand the material, not memorize the material. So the other thing that I've included in this class is worksheets. And each week you will be responsible for filling out your worksheets. I want you to know that the worksheets are very math intensive. They're math intensive because we're going to learn a lot of formulas in this first part of the book. There's lots of formulas, and we take those formulas, we apply the mathematics to them, and then we can start to see what the relationships are. In the end, we learn the formulas so we can learn the relationships. For example, we're going to learn in I believe next chapter or in the 3rd chapter, when frequency increases, when the frequency gets higher, the period of the wave gets shorter or lower. So those are inversely related. When one goes up, the other goes down. And those are the relationships that you need to know to help you understand how physics is working. But we also learn the formula for it. And so that's what we're going to kind of focus on in our worksheets. We're going to focus on those relationships and the formulas, doing the math for them. I want you to know, though, that for your boards and for my tests, you can't have a calculator. Okay, technically for my tests you could because you'll be taking them at home. but I won't put questions on there that you need to calculate 0.3457 times 67.92. Like, that won't be on there. It'll be what's 2 times 5. Do you know the relationship that this is going to cut in half? What's 4 divided by 2? Well, that's 2. You should be able to do some basic math in your head, maybe jot some things down, but it won't be anything calculator-wise. Your worksheets might need some calculators. So that is where I want you to understand the difference between worksheets are going to be more math intensive versus anything that I'll be having you do for your actual tests. All right, so that being said, let's get into our first chapter. It is a very basic chapter and just kind of covers some important things that we need to know for ultrasound. All right, so chapter 1, the basics, coming out of your book, Understanding Ultrasound Physics by Sydney K. Edelman. Now, one of the first things that we need to talk about are graphs, and hopefully this is going to be a lot of review for you. But with graphs, we have an X and a Y axis. So typically the X axis is our horizontal axis running side to side, and the Y axis is the vertical axis running up and down. Now, one of the axes that you might not be as familiar with is the Z axis, and the Z axis is actually what gives us our 3D world. We have that axis that comes kind of out at you from the page, and that is our 3D. Now, as we discuss different ways that ultrasound is mapped onto our screen, or some of the information is mapped like down in our spectral tracings, we need to remember what's shown along the x-axis versus what is shown along the y-axis. So it's important that we remember x is the horizontal part, y is the vertical part. Some other things that we're going to get into in this chapter 2 are definitions, and I mentioned this briefly just a little bit ago about how when we see those formulas, what we're actually learning are relationships. And so these next few terms are going to be related to relationships. And our first one is unrelated. And unrelated basically means that there are two variables, they have not one thing to do with one another. So I've got a couple examples here. We've got images on my phone and chairs at my table. I could have 300 pictures on my phone and 4 chairs at my table. Somebody else could have 2 chairs at their table and 8 pictures on their phone. They just don't have anything to do with one another. Same idea, chapsticks I have and color of my couch. There's just no relationship except for the fact that I find a lot of my lost chapsticks maybe in my couch, but that's a different story. Related then just tells us that there is some sort of connection between the two variables, but we're not defining what that connection is. So my examples again, money in my bank account and my happiness. Like, there's probably some relationship between that, but I'm not telling you that when one goes up, the other goes down, or maybe it varies from day to day. It has something to do with one another, but there's just no real relationship that is defined at this moment. So they're related, but we don't know how. Now, directly related and proportional is the first relationship that you're going to hear a lot of when we are learning about ultrasound physics. And directly related or proportional basically tells us when one thing goes up, the other thing must also go up. And when we say they're proportional, we mean that they go up at the same rate. So if the variable x goes up by, or doubles, then variable y will probably also double too, or some proportionality to it. So for example, we have the number of hours I work and my paycheck. That makes sense. The more hours I work, the more my paycheck is. The number of pages I read in my book and my knowledge, the more pages I read, the more I'm going to get from it. Number of times I come to Open Scan Lab and my proficiency score, the more you practice, the better your score is going to be. These are all directly related. And that little symbol that you see down in the corner there, that means that things are proportional. And you'll see that in a couple chapters here in one of our formulas. So the cool thing about directly related and proportional is that we can graph this. Remember, our vertical is our y-axis, horizontal is our x-axis. And let's use, for example, number of hours I work and my paycheck. So I work 5 hours, my paycheck is $50. We can graph that. Say I work 10 hours, my paycheck should now be $100 because they're proportional. Say I work 15 hours, then we've got a paycheck that's 150 hours. And we can graph these two variables and their relation together. What you will see then is that directly related relationships are going to have a map that goes in this direction. So if you're ever wondering, are these directly related or are these inversely related, what is going on, you can try mapping it out, see what happens with your numbers. That's a trick that you'll be able to use to help define your directly related versus inversely related. So as I was saying, we have maps for our directly related, or graphs for our directly related variables, and they're going to start in the lower left corner and angle their way to the upper right corner. Now the other term that you're going to hear a lot during this book is inversely related. And inversely related means when one thing goes up, the other must go down. So examples again, the amount of time that I use my phone. If I use my phone for a lot of hours, then my battery life is going to go down in it. The miles I drive in my car versus my gas tank. Gas tank's going to go down the more miles I drive. So these are inversely related. When one goes up, the other must go down. And just like we were able to with our directly proportional, we can also graph our inversely related variables. So let's use the phone one. So I've used my phone for 2 hours and I'm at 100%. After 4 hours, maybe I'm at 50%. Got a really bad battery. And at 6 hours, maybe I'm down to 25%. Again, you can see that we can graph these variables together, and you will see that these create a different pattern. They're going to start in this upper left-hand corner and work their way down to the lower right-hand corner. That is inversely related graphing. The other thing that you will see again with formulas is that some formulas just lend themselves to being directly related or inversely related. All three of these setups give us variables that create inversely related relationships. And you'll see this pattern when we talk about frequency and period. So here again is our graph of the inversely related variables. Again, it's going to start in that upper left-hand corner and angle down towards the lower right-hand corner. Now, reciprocals are a special inverse relationship, and it means that when two things are multiplied together, they are going to equal 1. So we have lots of examples on this page. 1/20 times 20 equals 1. 5 times 1/5 equals 1. 5 times 1/5 again equals 1. We can go down the list and you can see 3/4 over 4/3 or times 4/3 is going to equal 1. So the pattern that we're seeing here is that x times 1 over x equals 1. So again, we have our variable times 1 over the variable, that is going to equal 1. When this works out, that equals a, you guys can't see that super well. When that works out, that is going to equal a reciprocal. So we can just try another example here. Say x is 3. So 3 times what equals 1? Well, we just follow our pattern here. All we have to do is make that 1 over 3. 3 times 1 over 3 equals 1. And we can check the math on that too. When we have a whole number like this, 3, it's like writing it's 3 over 1. Times 1 over 3 equals 1. When we multiply across, we're just multiplying across, so it ends up being 3. 1 times 3 also equals 3. when you have a number that's over itself, that's the same as writing 1. That's how reciprocals work. The other thing that you need to be comfortable with doing, though, is we don't necessarily look at a number, say for example, 1/5. You're not going to be multiplying 5 times 1/5. You're usually going to do it in decimal form. So in your worksheet, you will see that you actually have a lot of practice in switching, taking a number, multiplying it by its reciprocal in decimal form. So this would be 0.2 times 1. So 5 times 0.2 equals 1, because 0.2 is the same as saying 1/5. So you're going to get some practice with that in your workbook. But be aware that you should know some basic decimal forms, like 1/3 is the same as 0.333 repeating, 1/2 is the same as 0.5, 1/4 is the same as 0.25. You should know some of those basic decimals. There's also a section in your workbook, or in your notes rather, that you are going to need to just be familiar with, and it is basic algebra on how to balance an equation. You're going to be given different variables of equations, and you're going to be expected to kind of figure out how to solve for each variable. So I want you to practice that or ask me questions through email. We can work on how to balance equations if you need that extra help, but that should have been covered in a basic algebra class. Now the other basic thing that we need to know, another basic thing that we need to know about physics and ultrasound, is that all numbers need to have a unit. You know, call up your friend and you say, hey, I'm going to be there in 5. You know, we know that to probably mean I'm going to be there in 5 minutes, but what happens if you showed up in 5 hours or 5 years? Your friend's going to be very confused. You said you'll be there in 5, but you didn't define it. And so that's really important when we're talking with numbers, that we define them somehow. So when we are discussing terms, you always, always, always must put a unit behind it. A lot of the units that we use in ultrasound are on the smaller side, so we use millimeters, micrometers, nanometers, microseconds, nanoseconds. We use very small terms. So, and we'll get into that a little bit, but make sure you're always using units. The other thing with units is that you want to make sure that you're using compatible units, and we'll talk about that again too in a little bit. The only exception to the rule of always having a unit is if you have a unitless number. And there are a handful of numbers that are defined as unitless. One of the numbers that we'll talk about in physics is called duty factor. That's just a number. The other thing that tends to be unitless are percentages, but then of course you will have the percentage symbol following. Now we talked about numbers in ultrasound, and that we usually use very small numbers, and that's when we're kind of talking more about measurements. But when we think about our ultrasound frequency, those numbers are actually really big. Megahertz is 1 million hertz. So we actually talk about some very big numbers as well. So we do need to spend a little bit of time about talking about powers of 10. So when we are looking at powers of 10, if an exponent is positive, then we're looking at a very big number that is larger than 10. When the exponent is 0, it's the same as saying that we are multiplying a number by 1, and then the number ends up being between 1 and 10. If the exponent is negative, then the number is less than 1 or a very small number. So let's take a look at an example here. We have 2.6 times 10 to the 6th equals 2,600,000. All we need to do is basically move that decimal point over 6 spaces. So let's look at that again. We've got 2.6 times 10 to the 6th. This is a positive exponent. So to expand our numbers out in the powers of 10, we're going to take our 2.6 and we're going to just move it over 6 decimal places. So we're going to go 1, 2, 3, 4, 5, and 6. Our decimal places now here, we can fill in our zeros and we will get 2,600,000. Let's do another example. Let's do 3.1 times 10 to the 4th. So again, we've got a positive number up here, which means this, whatever number we come up with, should be greater than 10. So we're going to write our number down, and we're going to move that decimal point now 4 spaces. 1, 2, 3, 4. Fill in our spaces with our 0, and now 3.1 times 10 to the 4th is 31,000. So that number is definitely bigger than 10. So this way of writing right here, this is called scientific notation, and it's a way of writing very big numbers in a more truncated form. 3.1 times 10 to the 4th is also the same as saying 3.1 times 10,000. So when we are using those exponents, that's actually another shortened way of writing large numbers too. Let's do one more example. Let's do 1.8 times 10 to the 9th. So again, we write down our 1 and our 8, and we're going to move that decimal point to the right 9 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9. We fill in our zeros. Now we have a number that is 1,800,000,000. So it's a very large number written in a shortened form. Now what does it mean to expand the numbers when we have a negative exponent? Well, it's very similar to expanding in a positive way, except we're going to move the decimal point to the left. So in our example, we're using 2.6 again, and we are multiplying it by 10 to the negative 6th. And so we move that decimal point 6 places to the left to get our expanded number. So let's take a look. We have 2.6 times 10 to the negative 6th. Now remember, that's a negative number, so this has to be a number that's less than 1. When we have negative exponents, they are going to be decimal numbers. So we'll take our 2 and our 6, and now we're going to move that decimal point 6 places to the left. So we have 1, 2, 3, 4, 5, and 6. Always put your beginning 0. 1, 2, 3, 4, 5 zeros in there to fill in those blanks. And now we have our new expanded number. We can do another example here. Let's do 4.3 times 10 to the negative 2. So again, this is a negative number. This means that this number will be less than 1. And the other thing I want you to notice when we're writing in scientific notation, look at this number. This number has always been between the numbers 1 and less than 10. So it can go up to 9.999999. But it should be a number between 1 and less than 10. So we can write down our 4 and our 3. We're going to take our decimal point, 1 spot, 2 spots, and that is it. So once we move those over the 2 spaces, now we have 0.043. So you'll have a little bit more practice to do with this in your workbook. Please let me know if you need more help with expanding powers of 10. Now when we're expanding to a 0 exponent, it's like saying the same thing. So when we have 2.6 times 10 to the 0, when I say it's like saying the same thing, 10 to the 0 equals 1. So it's like we're saying 2.6 times 1 is going to equal 2.6. Whenever we have an exponent that is 0, it is going to be equal to the number that we originally were multiplying by. Now when we need to convert back to powers of 10, we're going to kind of do the opposite. When we start with a very large number, the first thing that we're going to do is write it into a number that is somewhere between the numbers of 1 and 10. We can then count the spaces that we need to go back, and that gives us our exponent. So let's do the example on the screen here on our board. So we have 3, 4, 1, 2. So we have 3 billion, and we want to make that into a powers of 10. I'm just putting this trailing 0 here for visual purpose. But what we are going to do is take our leading numbers. We need to make a number that is somewhere between 1 and 10, but it can't be equal to 10. And then we're going to count the spaces for our decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9. So now we know that we are multiplying 10 to the 9th. And that is how we would expand that out. Now we can do the same thing for converting very, very small numbers. We will take the number, figure out where a number is between 1 and that is less than 10, and then we'll count the decimal spaces that we needed to convert the number to a power of 10. So back to our example, 0.00049. We're going to take that 4 and the 9, that's our number between 1 and 10, and we're going to multiply it by 1, 2, 3, 4. 10 to the negative 4th exponent. Remember that negative when we are working with decimal numbers. When we have a number that's greater than 1 but still less than 10, and we need to write that into scientific notation, we are then just going to take the number and multiply it by 10 to the 0, because we remember that 10 to the 0 equals 1. Another concept that's going to be very, very helpful in understanding physics and how to use the formulas is understanding how the metric system works. Now, the metric system is based on powers of 10. So when we have a unit and it's at its base, so our bases are units like meter, like grams. I was blanking out there for a second. So meter, grams, liters, those are all base. And it would be the same like saying it is the unit times 10 to the 0 power, which is 1. So bases are going to be anything that is just the unit itself with no prefix added to it. So our example here is 1 times 10 to the 0 meter would be the same as saying 1 meter. But we need to be able to convert from our base to very large multiplications of our base or to very small multiplications of our base. So we're going to start with those large ones. When we want to get into a larger number than our base, we are again looking at powers of tens. So if we have 1 meter times 10 to the 3rd, that'd be the same as saying 1 kilometer. It's the same as saying 1,000 meters. 1 million meters would be the same as saying 1 times 10 to the 6 meters, or 1 megameter. So it's when we start adding those prefixes that we get new units based on powers of 10. As I had mentioned, we can go the other direction then too. If we have 0.000001 or 1 millionth of a meter, that's the same as saying 1 times 10 to the negative 6 or 1 micrometer. 0.001 meter or 1,000th of a meter is the same as saying 1 millimeter. So we can see why learning what the powers of 10 are is going to be helpful for when we start to convert units in the metric system. And this chart here is going to be very helpful for you to kind of visually see all of it. It tells us what type of exponent we're working with for each prefix, what the prefix is, the symbols that we use for it, and the meaning as well. For example, if we wanted to write down 1 gigaliter, it'd be 1. If we wanted to abbreviate it, it'd be 1 gigaliter. And that is the same as saying 1 liter times 10 to the 9th. Or the same as saying 1 billion liters. So 1 billion liters equals 1 kiloliter. So being able to convert through this is going to be very helpful. A lot of times we're going to talk about our frequency in hertz, but then our actual frequencies that we're using in ultrasound are some sort of megahertz derivative. Same thing with time. We use second, our base, as a very common base, but then when we relate this back to ultrasound, we're quite often talking about microseconds. So we need to be able to convert to keep our numbers and formulas correct. We also want to make sure that when we are converting units that we are using consistent units. So if we have a formula that uses all megahertz, then we should probably be also using formula that includes microseconds. And that's because mega and micro go together. So you want to make sure that you are using complementary units when you are changing units around. So we are going to practice a lot of converting because you're going to be doing a lot of this throughout your time of learning ultrasound physics. And that's solely just because we're going to be getting different formulas with different information that we want in the end. Maybe our whole formula solves for hertz, but we want to tell it in megahertz because that's what we're operating in. So it's going to be important that you know how to convert. One of the more common conversions that you'll often do is when you're measuring something on your ultrasound machine. A lot of times it'll get measured in either millimeters or centimeters, but then your doctor might want it reported in the opposite. So maybe your machine measures centimeters, your doctor wants everything in millimeters. You need to know how to convert between the two. That's probably the most common conversion that you'll do day to day. Physics-wise, though, we do need to know how to convert between different things. So I've got a few examples here. I've got them all written down on the slide, but I'm going to go to the next slide here, and I want to show you real quick what I call the metric staircase. And so I think one of the really big things that would be very helpful when you are writing this is just to kind of get used to writing out your metric staircase. And so what I often do is make my base, and then when we go up, we go up 9 stairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we also go down 9 stairs. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so if you draw your stairs out, I'm going to go to my drawing here. If you draw your stairs out, just make sure that you're drawing them all in, because what's kind of tricky about this is that after we do deca, hecto, and kilo, we skip 2 stairs, and then we have mega, skip 2 stairs, and then we have giga. So make sure you're skipping those stairs. Don't just go DHKMG because you're going to mess up your stairs. Same thing with going down. This was our base. We have deci, centi, and milli. Skip 2 stairs, and then we have micro. Skip 2 stairs, and then we have nano. So sometimes I write out my stairs completely. Sometimes I just do base and then DHK -M -G, and then we can do DCM -N. So I vary how I write my stairs. It all depends on how much space I have. Sometimes if I know I'm only converting down the staircase, I might only write the lower half. If I'm converting up the staircase, I might only write the upper half. So it kind of depends on my space that I'm having to write in and which direction I'm converting. But I think the staircase, getting that memorized so you can convert anything that you need to, is going to be very helpful. The other thing that you need to remember is that when we are converting down the staircase, we are going to move our decimals to the right. And so I think of that as I'll be right down. Okay, so moving your decimal to the right when you are converting down the staircase. So that would be an example of that would be like if I wanted to convert from gigas to megas, or if I wanted to convert from decis to millis. Okay, I'm going down the staircase. I'm going to move that decimal to the right. I'll be right down. If we wanted to convert up the staircase, we're going to move the decimal to the left. And I think of that one as if it was up left to if it was left up to me ... So that's how I remember it. I'll be right down. If it was left up to me, I'll be right down makes more sense because you're coming down the staircase, helps you out a little bit more. But so this example would be like, say we wanted to convert from our base to a kilo, or if we wanted to convert from nano to micro. So that would be going up the staircase. We move our decimal to the left. So we can do a few examples of these. I'm going to pull the examples from that slide that we were just previously looking at. So the first one says that we have 1 million liters. How are we going to convert that to megaliters? So we can use our upper half of our staircase. Remember, we have our base, which is liters in this case, and then we have deca, heca, kilo, 2 stairs, mega, 2 stairs, giga. So I am converting from liters, which is our base, to mega. So we're going to count the stairs. We're going to go 1, 2, 3, 4, 5, 6. That was 6 stairs total, meaning that I have to move 6 decimal places to the left. So I'm going up the staircase. If it was left up to me. So we're going to take our 1 million. The decimal places here, or the decimal starts here, and we're going to go to the left 6 spots. 1, 2, 3, 4, 5, 6. So 1 million liters is the same as saying 1 megaliter. All right, let's try another one. Next one down the page then is we have 1 million decaliters. And we want to know how many megaliters does that equal. So again, let's write our upper half of our staircase. We have base, deca, hecto, kilo, 2 stairs, mega, 2 stairs, giga. This time we're starting at deca, so we're starting here this time. And we're going to count up the stairs, 1, 2, 3, 4, 5 to get to mega. So now we need to move the decimal 5 spaces to the left because we went up the stairs. So let's write our 1 million down here again. Remember our decimal point starts at the end here. We're going to move 5 spaces. 1, 2, 3, 4, 5. So now we can say that 1 million decaliters is the same as having 10 megaliters. Let's try converting down the staircase here. And we're going to stay on the upper half for this example. So now, actually, nope, we're converting down the staircase regardless. Okay, so now we're going to the bottom half of the staircase. So we're going to start with 1 liter. We want to know how many deciliters does that equal. So we're going to write my base. Remember, we go deci, centi, milli, 2 spots, micro, 2 spots, nano. So we started at our base. We're going to go down to the deciliter, and we're going to count. Oh, just 1. So we're going to move our decimal point 1 spaces to the right because I am going right down the staircase. So here's our 1. The decimal starts there. 1 spot to the right, fill in our 0. 1 liter is the same as saying 10 deciliters. All right, one more example from that page then, and then you're going to have lots of practice of this in your workbook and for the rest of your ultrasound physics career. One thing I will point out to you now, that there are instances on tests and quizzes and on your boards that they will put a bunch of different answers down. They'll give you some answer and then they'll give you like 25 kilohertz, 5 hertz, 8 megahertz, and it'll say like put these in order or which one is the highest, and you're going to have to convert these. You're going to want to convert them all to the same. So you'll say, it'll be 5 hertz, it'd be the same as saying 25,000 hertz, and this would be the same as saying 8 million hertz. So it's going to be helpful to always convert into one consistent unit when you are faced kind of like with a question like that. So don't just choose the number because it's correct. The unit matters just as much. It really changes what that value is. All right, last example from that previous slide then, we have 1 milliliter, and we want to know how many microliters does that equal. So let's write our staircase. Again, we have our base, deci, centi, milli, 2 stairs, micro, 2 stairs, nano. All right, our question is saying we have 1 milliliter. We want to know how many microliters. Let's count how many stairs we have to go down. 1, 2, 3. We went 3 stairs down. So that means we're moving our decimal places 3 spots to the right. So we'll write our 1 down. Our decimal place, our decimal starts here. 1, 2, 3. Fill in our zeros. 1 milliliter is the same as saying 1,000 microliters. All right. So that kind of gives you an idea of how to jump in between the stairs and then how to figure out how to change over your units. Again, I still have to do this when I'm writing out equations sometimes, or if I want to just double check that I'm doing it. The more that I practice it, the quicker I am at just kind of figuring it out. If you've got a strong mastery of this, you may not have to write it down and you can just kind of figure it out in your head. But I think for a lot of us, it's going to be a matter of needing to have that visual representation of how to convert up and down the metric units. So again, this staircase is in your workbook. This is one thing that I would just memorize so you can do it right off the top of your head. If you're taking a test, jot it down. It'll be helpful for you for changing over. All right, and that is the end of chapter 1. So hopefully this was an excellent introduction. Remember, we still have chapter 2 and chapter 3 left of this unit. You will want to finish those videos before you start your workbook. And then once you get your workbook done, remember to share it back with me so you get credit for it. If you have any questions, please email me. I'd be happy to answer your questions through email, through video. We can do online office hours if that works. We can do it over the phone if you would prefer that. Or you can also submit questions through our classroom as well. So you have lots of options. Please let me know if there's anything that is unclear. and that I can try to clear up for you.